Let's turn to the next section and talk about the tools astronomers use and properties of light, how we detect it, collect it, and focus it. Here's a rough outline of the topics we are going to cover. They include the nature of light, the electromagnetic spectrum, thermal radiation, spectra, the Doppler shift, collecting, detecting, and focusing light. Let's start by looking at the dual nature of light. What do we mean by dual nature? Well, to ask that question, let's first ask, what is light? Light can be looked at as a form of radiant energy, which travels extremely fast. 300,000 kilometers per second, in fact. Light can actually be described either as a wave or a particle depending on the circumstances. It sometimes exhibits properties of both. When we look at light as being a wave, we can talk about things such as wavelengths or frequencies of the wave of light. When we think about light as a particle, we can think about small packets of energy or quanta of energy called photons. We mentioned last time that distant objects appear dimmer than the amount of radiant energy they actually give off. And we said that how dim they appear has to do with how far away they are squared. In other words, if you were to place the Earth twice as far away from the Sun as where it is now, the Sun would appear 2 squared or 4 times dimmer. Light is part of what we call the electromagnetic spectrum. The electromagnetic spectrum encompasses all different forms of light, from radio to X-ray and visible light in between. The light that we see, the visible part of the spectrum, is a very, very tiny fraction of the entire electromagnetic spectrum of light. When we think of light as a wave, we can discuss its wavelength. The wavelength is the distance from one wave crest to the next. It is generally indicated with a Greek symbol lambda. Wavelengths of light that we see are very small, in the nanometer range. The redder the light is, the longer the wavelength. The closer to blue or violet the wave is, the shorter the wavelength. Instead of discussing wavelength, we can talk about frequency. This has to do with the amount of time that passes between one wave and the next. How frequently does one wave hit one spot? That is a measure of the frequency of a light wave. If you multiply the frequency times the wavelength, you end up with the speed of light. When we think of light as a particle or a photon, we can use the information we have about its wavelength or about its frequency to determine how much energy each photon carries. In other words, the amount of energy a packet of light carries or a quanta of light carries has to do with its wavelength or its frequency. This is why if you get ultraviolet rays striking your skin, you can get a sunburn. But if you were to put your hands under a heat lamp without much UV radiation, it would not be as easy to get a sunburn. This also explains why X-rays penetrate the skin and allow us to see the bones inside. These high energy rays, such as X-rays, can be very damaging to us because of the amount of energy they carry. So in other words, while very high frequency wavelengths, high frequency light carries a lot of energy, i.e. short frequencies of light carry a lot of energy. The light we see carries less energy. Visible light consists of what we typically think of as white light. But as you might know from seeing a rainbow on a rainy day or having put light through a prism, white light actually consists of various colors. The colors we see may seem to have a large range to them, from purple all the way to red, and every shade in between. But as I mentioned earlier, visible light only comprises a very small part of the entire electromagnetic spectrum. This diagram is a synopsis of the entire electromagnetic spectrum. And you see that visible light is only the small rainbow, which is blown up at the bottom so that you can see it a little better. To the right on this diagram are longer wavelengths. Those are on the redder end of the spectrum, such as radio waves. To the left are shorter wavelengths, high frequency, highly energetic waves of light, such as gamma rays. Now let's move on to the topic of thermal radiation. We tend to think of temperature and heat as being the same, but they are actually different. Heat is a way of transferring energy, whereas temperature is simply a measure of the motions of the atoms and molecules within a substance. The faster the atoms and molecules are moving, the higher the temperature of the substance or object. Temperature can be measured in a number of ways, on a number of different scales. We're very used to, in America, using the Fahrenheit scale. Most of the rest of the world uses Celsius. However, astronomers tend to use a temperature scale called Kelvin, where 0 degrees Kelvin is what's known as absolute zero. Nothing can really be colder than absolute zero. At this point, the atoms are not moving at all. Another tool that will help us explore thermal radiation is a model called a black body. A black body is an idealization. It is the idea that a perfect substance would be able to absorb all the energy that is incident on it and also be able to emit all of that energy back in all wavelengths. Stars and the sun can be looked at as approximate black bodies. As we will see later, they are not perfect black bodies. For a perfect black body, the spectrum is a smooth curve. In other words, yes, it does give off radiant energy in all wavelengths, however, not in all the same proportions. Instead, a blue object is blue because most of the radiation that it gives off is in the blue end of the spectrum, whereas a red black body would give off most of its radiant energy in the red end of the spectrum. Notice too that the bluer an object, the brighter it appears. As depicted here, we have the wavelength on the x-axis and the brightness of the black body on the y-axis. So you see for the blue curve that the peak of the curve is higher in the brightness, but closer to the blue end of the spectrum towards the left on the x-axis, whereas the peak of the red black body appears lower on the y-scale, i.e. less bright, but farther down towards the right end of the spectrum in the red region on the x-axis. When objects heat up, they also change colors. Because blue is a more energetic form of light than orange or red, we know that it must be a hotter object. To summarize these 2 points, we have Wien's law and Stefan Boltzmann's law. Wien's law basically says that hotter an object is, the more strongly it will emit light at shorter wavelengths, or the bluer end of the spectrum. The reverse of that would be that the cooler an object is, the more strongly it will emit light at the redder end of the spectrum. Stefan Boltzmann law says that the more luminous something is, must indicate that it is higher in temperature. There are equations that go with this. If we are able to measure the exact wavelength, which is at the peak of the spectrum, where the most radiant energy is given off, we can call that lambda maximum. Once we know lambda maximum, we can take a constant and divide it by lambda maximum to come up with the temperature of that object. Stefan Boltzmann law allows us then to take that temperature, take it to the 4th power, and multiply by a different constant to determine the luminosity, how much radiant energy the object gives off. Using Stefan Boltzmann law has allowed us to determine that the sun outputs about 64 million watts per square meter. Let's talk more about spectra, and how atoms interact with a spectra of light. We've already decided that the electromagnetic spectrum is a very large range of light. Visible light comprises a small part of this. When we split visible light, we see the different colors that it's made up of. But if there were some cooler object in between our light source and our prism, then certain black chunks would be missing from our spectra of light. This is due to the fact that the photons interact with the atoms in the cool gas, and those atoms absorb some of the light. So there are several different types of spectra then. There is the continuous spectrum, which would be the case if everything was a perfect black body. It would look like the smooth curves that we saw earlier, or it would look like Exhibit A if we broke it into colors. Then there is something called an emission spectra. An emission spectrum is when a particular atom or molecule actually emits light at certain wavelengths, giving us a dark background with light lines imposed. This is like example B. But in stars, what we see is like example C, an absorption spectrum. This looks like a continuous spectrum, only with black lines or chunks taken out of it at various wavelengths, which correspond to atoms or molecules absorbing that wavelength of light. Here's what the sun's spectrum looks like. If you look very closely, you will see dark lines on top of an otherwise continuous spectrum. If we write those dark lines a little differently, like on B, then we can examine exactly what wavelengths they are located at. It turns out that the wavelengths that are taken out of the spectrum, these dark lines, correspond to different elements that are in the sun. Here's the composition of the sun as we know it from being able to examine its spectra. You see that the majority of the sun is hydrogen. A good bit of it is helium, but there are also other elements present in the sun. What can light do if it's moving? Let's think about the Doppler shift for a moment. The Doppler shift you may be familiar with in terms of sound. If you've ever heard a train or an ambulance approaching, as its siren is blaring or whistle blowing and it's coming towards you, it sounds as though it has a fairly high pitch. But after it passes you and it's now traveling away from you, its pitch sounds lower. Light does a similar thing. If it's moving towards you, its frequency is higher. If it's moving away from you, its frequency is lower. Higher frequency means a bluer color. Lower frequency means a redder color. It's important not to get these two things mixed up. If something is heading towards you, we say it is blue shifted. If something is heading away from you, it is red shifted, because it appears redder. If it's difficult for you to remember this, I came up with a mnemonic. Well, it's not actually a mnemonic, it's just a saying. And you could think of it this way. Red runs away, blue comes to play. In other words, blue is heading towards you, blue shifted. Red is heading away from you, red shifted. Most objects in space are moving in many different directions. Perhaps they're coming towards us, perhaps they're receding away from us, and they're also usually spinning. We can measure the rotation rate of stars based on Doppler shift. But how do we detect all of this light? Generally, we use telescopes. Telescopes have been around for a long time, and in the past, it was traditional to look through the telescope with your eye and draw pictures of what you saw. However, as technology progressed, the eye was replaced with a camera. Cameras are more sensitive to the human eye and less likely to give us error. Today, we use CCDs instead of eyepieces on most research telescopes. Before the CCD camera was invented, people used glass plates. A CCD records the photons that hit it. It is very sensitive to light, in fact. We can also use telescopes to observe wavelengths that we cannot see. Telescopes with X-ray capability, gamma ray capability, and infrared capability are in orbit outside of the Earth's atmosphere. This is important because the Earth's atmosphere does absorb certain wavelengths of light, making it harder to see those things if we were to keep the telescopes on the ground. Let's talk more about how we collect the light in a telescope. We need to be careful to be very precise with our telescope and very exacting with our standards. Different wavelengths of light require different things. Radio telescopes, such as this one, need to be very large in size, because the wavelengths they are collecting are also very large in size. And also, the larger the size of our collecting area, the better off we can see things. This allows us to collect more light and focus it more clearly. Oftentimes, we select certain wavelengths of light through filtering so that we can examine just that part of the electromagnetic spectrum. How exactly do we focus the light then? There are a number of different ways that we can use optics to focus light. The first way that telescopes used optics to focus light was through a phenomenon called refraction. This occurs when light is actually bent. How can light be bent? Well, this happens because the speed of light is not the same in all medium. Light traveling through air is able to travel faster than light traveling through glass or water. Therefore, when the light wave hits the interface between air and glass, then the part of the beam that hits the glass first has to slow down before the part of the beam that hits it afterwards. This causes the light wave to bend. You may be familiar with this phenomenon when you see a straw in a glass of water which appears to be disconnected to the part of the straw which is out of the water. This is due to the refraction of the light in the water. But not all wavelengths of light are bent in the same way. Because some wavelengths are bent differently than others, what ends up happening is a smearing out or blurring effect called chromatic aberration, which is inherent in any refracting telescope. A refracting telescope does use the phenomenon of refraction and a lens of glass to bend the light rays to a focus. It's not a perfect focus for all colors because of chromatic aberration. Large refracting telescopes are very difficult to build and very heavy. What you see pictured here is the Thaw telescope at the Allegheny Observatory in Pittsburgh, Pennsylvania. It is a 30-inch refracting telescope, which at the time was one of the largest telescopes ever built. It is so immense that it sags under its own weight, and it's difficult to support and to maneuver. Because of these problems and the finite size to which we could build refracting telescopes, a different idea was come up with, and that is the use of mirrors to reflect light instead of the use of lenses to bend it. John Brashear, who worked at the Allegheny Observatory, pioneered a method to safely polish telescope mirrors. Prior to his method, the process of creating mirrors for telescopes could be dangerous. The chemicals involved could lead to explosions. Once the technical difficulties were sorted out, Mirrors became very popular to use in modern telescopes. This is partly because they can be built very, very large. We don't require a very thick piece of glass for the light to go through, and so it is easier to support a mirror and build a larger telescope. And a larger telescope means more light collected and more distant objects we can see. There are a few different setups to a reflecting telescope because they all involve a secondary mirror to bounce the rays back towards a camera or an eyepiece. The camera can actually take place inside of the telescope in a prime focus reflecting telescope, or it can be bounced off of a secondary mirror in a Cassegrain style or a Newtonian focus style. What you see here is the 16-inch RCX Meade 300 telescope at the Allegheny Observatory. You see it pictured here with an eyepiece on, but typically it had a CCD camera attached to it. You see that this telescope is much smaller than the thaw we saw earlier at the same observatory. However, this is a telescope that was used primarily for my research and continues to be used for the research that is ongoing at the Allegheny Observatory, because it is much easier to use than the refracting telescope. If we piece mirrors together, you can make an even larger telescope. The Keck uses 36 mirrors as one big mirror.